Hello and welcome back to Machine Learning. I'm Jivita Christie, and in this video, we are going to talk about clustering, and we will be seeing the K-means clustering algorithm. So let's begin. First, let's understand what clustering is. We know that clustering is an unsupervised machine learning technique because we saw that earlier in one of the videos. And now we're going to see what exactly it is. So think that suppose that you are invited to take a session on machine learning in a reputed university for induction of their professors on the subject. Okay, but before you create the material for your session, you want to know the level of acquaintance of the professors on the subject so that the session is successful. So you want to know beforehand how acquainted the professors are, how much of machine learning do they already know, so that you can prepare a better session, a successful session. Okay, but you don't want to ask the university that is inviting you to give a talk. You don't want to ask them about how well acquainted the professors are, but you want to do some analysis on your own based on some data that's freely available about all these professors online. So what happens in machine learning? It is an intersection of statistics and computer science. So you are more focused on the professors which are there in these two areas, okay, computer science and research papers into statistics, computer science, and machine learning. So you want to put them into three different buckets. You want to classify the professors into three different categories: statistics, computer science, and machine learning, based on the research papers you found. So you will do that on the basis of how many papers they have written. Okay. So you'll see how many statistics related publications they have and how many computer science related publications they have. So you have your X and Y axis given here, and you'll plot all the data. So each dot here represents a professor. And you can clearly see there are three clusters forming. So you can say that these ones, this cluster right here, are the people who have less number of statistics related papers, but more number of computer science related papers. So they must be computer science professors. But then there are statisticians who have written a lot of statistics related publications, but they have not published much in computer science field. So you know that this group is a statisticians group. But then there's also this group right in the middle who have written an equal number of computer science papers and statistics related papers. And so you can say this group would be a machine learning expert group. And now you know, you've gotten to know all the professors who are going to attend your session. So this was possible using clustering, and there are many techniques for performing clustering, and some of those are given here. So we have partitioning methods, that is one of the techniques. We have hierarchical methods and density-based methods. So there are three clustering techniques: partitioning, hierarchical, and density-based methods. So what happens in all those? So in partitioning methods, you have to use the mean or midoid to represent cluster center. So you probably already know what mean is. It is the average, right? So if you have a cluster of points, you will just take the average of those points and find the center for that. But in midoid, what you do, you find the center point. You find one of the points you pick as a center. And that's what you do in partitioning methods in mean and midoid. It adopts a distance-based approach to refine the clusters, which means once the center is found, it will try to do the clustering based on distance from that center. It also finds mutually exclusive clusters of spherical or nearly spherical shape. and it is great for working with small to medium-sized data sets. The next one we saw was hierarchical methods, which creates a hierarchy or a tree-like structure by decomposition and merger. Okay, so here clustering is happening by creation of a tree. So you begin with a root node, try to separate the root node into two different clusters, then separate those two clusters into more clusters. And once again, you are using the distance measure between the nearest or furthest point in the neighboring clusters as a guideline for refinement. Okay. And one of the disadvantages of a hierarchical method is that if you have some erroneous merges or splits, you cannot correct them in the subsequent levels. So if you have merged two clusters or split two clusters on that level, you won't be able to correct that in the next level. So once it's done, it's done. And the third kinds of methods we have are density-based methods, which are useful for arbitrarily shaped clusters. So partitioning methods and hierarchical both work with sort of spherical shaped clusters, but density based can work on any kinds of clusters with any arbitrary shape. But the guiding principle of this cluster creation is the identification of dense regions of objects in space, which are separated by low density regions. So just as we saw previously, we saw this space that was filled with data points, and then there was this white gap where there was no data point. So based on that, you can identify based on density. And if there are outliers, they can just get filtered out because they are not belonging to any cluster, they are far away. Okay. Now let's talk about the partitioning method. And in the partitioning method, the first algorithm we are going to look at is the K-means clustering algorithm. And in the next video, we'll look at the other one, which is the K-medoid algorithm. So what happens in the K-means clustering algorithm? In the first step, you will select K points in the data space and you will mark them as initial centroids. And there are ways to select these K points, okay? So it depends on how many clusters you want to make. If I want to divide my data into 3 clusters, I will select 3 points in the space, okay? And if I want to make 4 clusters, I'll select 4 points. So it depends on how many clusters you want. So based on that, you can select K points. Once you've done that, then you're going to repeat these steps in a loop. The first step of the loop is to assign each point in the data space to the nearest centroid to form K clusters. Okay, so now that you have K centroids, you will see what the other points are. Okay, where can the other points belong to? Which centroid is the closest for all the other points? And in that way, you will assign one cluster to each data point available. Next, you're going to measure the distance of each point in the cluster from the centroid. So now you have all these points in your cluster. So you will measure the distance of every point in your cluster from the centroid because you have divided them into clusters now. Then you will calculate the sum squared error, which is SSE, to measure the quality of your clusters. So this SSE is something we will see in the end. I will show you the formula for it, but basically it just gives you it's a measure of how much error is there. Okay, if this is very high, SSE is very high, then that means you have more error in your clustering. Next step is to identify the new centroid of each cluster on the basis of distance between points. So initially you just picked K points randomly, but now that you have divided everything into clusters, you can get new centroids based on the divisions that you have done. And once you get new centroids, you will once again apply all the steps from 2 to 5 and get even newer centroids. And you will go on doing this till you stop getting any more new centroids. So that means you have reached the correct value of your centroid, and that's why you're not getting any more centroids. So that's where the loop ends, and this is how the K-means algorithm works. Now let's take a look at some strengths and weaknesses of the K-means algorithm. So the advantage is that the principle used for identifying the clusters is very simple. and it involves very less complexity of statistical terms. So this algorithm is very easy, and it's also very easy to implement and to understand. It's also very flexible, so you can adjust it for most kinds of scenarios and complexities. And also the performance and efficiency of this algorithm are very high compared to the sophisticated algorithms, other algorithms which are sophisticated, and yet this one's so simple and yet has such high efficiency. The disadvantages are that it involves an element of random chance, right? Because in the beginning, when you're defining your k number of centroids, you are picking points randomly. So it depends on that random chance. Okay. And the starting point of guessing the number of natural clusters within the data also requires some experience, because when you create a scatter plot out of your data, you may or may not be able to tell how many clusters can be formed. So you also have to be experienced in K-means clustering to identify how many clusters can that data be divided into. Now let's talk about how you can determine the value of K so that your algorithm is optimized. So usually for a small data set, we use K is equal to n by 2. So if you have a very small data set, maybe 1000 rows, then your value of K will be just 1000 by 2, which will be, of course, it's very high, but that's how this is 1000 by 2 and then root. So you take 1000 divided by 2, which is 500, take a square root of 500, whatever you get, that will be your value for K, okay? But unfortunately, this does not work well if you have a large data set, because then you will have a large value of K and you really don't want that many clusters. But there are many ways to select the value of K. One such way is the elbow method. In this method, you try to measure the homogeneity or heterogeneity within the cluster for various values of K, and then you arrive at an optimal value of K. Okay, so homogeneity or heterogeneity is about how much similarity or dissimilarity is there within each of the clusters, and then by trial and error, you can arrive at an optimal value for K. So this is an example. So you can see this, these are the data points here, okay? And this is known as within group homogeneity. So similarities are there, and you can see the curve is moving upwards, and this is the elbow point. So the elbow point shows you that after a certain time, after a certain area, this curve is almost a straight line. So you can see here it is steep because it's increasing, but then here it is almost equal. It's almost constant, right? So that's why you can see this is the elbow point. And if you take a look at this graph, this is also a curve that's moving upwards. But in this case, after this point, the homogeneity increases. Okay, that means after this point, the points are closer to each other. They are getting more and more similar. So you can say this is your elbow point. Now, what is SSE? So SSE stands for sum of squared errors, which we saw earlier. And I told you I'll show you the formula. So this is the formula for it, okay? Here, the distance is the Euclidean distance. We have talked about this as well previously. So distance is the Euclidean distance between the centroid, which is Ci, and the data point, which is x, for which you're calculating. And so you will calculate this distance for all the points that you have in your in one particular cluster, and then take a square of all these distances and add them. That will be your SSE. And the idea is to have a cluster where SSE is minimized. And if you were wondering how to calculate Euclidean distance, this is how you can do it. So Euclidean distance is this, sigma xi minus yi whole square for a data point xy. Now we're going to implement the K-means clustering algorithm in Python. To implement the K-means clustering algorithm, you need to import all these libraries. So first we have the pandas library, of course. We also have the NumPy library this time. We will also be plotting the result using matplotlib. So we are importing PLT as well as Axis 3D because we will be creating a 2D graph as well as a 3D graph. And to implement K-means clustering model itself, we will be importing K-means from sk.learn, sorry, from sklearn.cluster. And the file that we are using, the CSV file, is this file on several kinds of spine related data. Okay, so the spine is sort of a backbone that people have, and this data is used to find out if the spine is abnormal or normal for different kinds of people. Okay, so there are a couple of things here. The first thing is the pelvic incidence. Now all these are just values for different organs or body parts in your body, and so um, these values are very biological. We don't need to understand what exactly these values mean, but based on all these values, you can decide if the spine is normal or abnormal. So we are just going to perform clustering on this data. So what we have here is pelvic incidence. Um, we also have pelvic tilt, and we have a lot of things, but from there, we are going to use three. One is pelvic incidence. So I'm getting all the values of that column. I'm getting all the values of the pelvic radius column, and I'm getting all the values of the thoracic slope column right here. And based on these three, we will try to perform a clustering. Okay. So F1, F2, F3 are the three features I have selected. I'm going to put them into a NumPy array in this manner. Okay. Once they are put inside, I now want to create my cluster. I want to apply the K-means clustering algorithm. So to do that, I'm going to use the K-means function, which I imported earlier, and create an object called K-means. And here I will define how many clusters I want. So I want 3 clusters. So I'm writing n underscore clusters equal to 3. And the random state is 123. So I want this to be done randomly. Because in K-means clustering, the first iteration takes the clusters randomly. It selects the clusters randomly. So that's why there is a random state measure of randomness mentioned. Once this is done, now I want to fit my data onto it. So I have this X, which contains these 3 columns that I have picked out, and I want to fit that data into my K-means algorithm. So I'm using the dot fit function in the object that I created earlier. Once it is done, now I want to make a prediction about what data falls into which cluster. Remember, I have 3 clusters. So I want my data to be divided into 3 different clusters. And to do that, I will use the dot predict function and pass X into it and get my cluster labels because I want 3 clusters, okay? And you can also find the centers of your clusters, okay? So those centers can be found in this manner. You will use k-means.cluster underscore centers underscore. So this will give you 3 centers because we wanted 3 centers in our, we want 3 different clusters. So we have 3 centers and we have 3 columns as well, which means if we try to plot this data, it will not be 2D. 2D would mean there would be 2 columns, but we have 3, and that's why we have to plot it in a 3-dimensional space, which is why you are getting 3 values for each center. Okay, so these are the 3 values for each center. This is the value for pelvic incidence. This is the value for pelvic radius. This one is the value for pelvic thoracic slope for the first center. Okay, so these are the centers, and to understand this better, we can plot it out. So here we are plotting it in a 2D space. So in a 2D space, we are trying to first, of course, you must be familiar with this. plt.figure will create this figure, and we are creating a scatter plot of x and of x values. So we are passing into it 0 and 1. So remember, x is the array we created here. So when I'm saying 0 and 1, that means I'm trying to pass over here the first 2 columns, and I'm trying to plot those 2 columns here. So I'm plotting those 2 columns here. and I will be plotting the centers as well. So these stars that you see are the centers which we created, and I'm writing here marker equal to asterisk, which means it will be printed in the shape of a star, as you can see, yellow star. Okay, so this is what it will look like in a 2D space. But if you want to plot it in a 3D space, then it will look like this. Okay, so in a 3D space, we are again using the PLT, but this time we are using the Axis 3D, which we imported earlier. And in the scatter plot, we will pass all the three columns and all three centroids and mark them with a star. And we can also specify color if we like. So this is what it will look like in a 3D space. So that's how K-means clustering works. It will divide your data into clusters, and it's very easy to implement, very easy to also understand. So I'll see you in the next video. Thank you for watching.